Welcome back, y'all. We are in Engineer 11 right now. We're on Class 8. This is Wednesday, the 29th of January. We are coming back to Lesson 3. This is actually going to be, the work that we're doing right now is actually the third session that we've had in Lesson 3. We're focusing on storing and manipulating unsigned integers. Last time we spoke about what we call the general decimal digit representation. So this is going to be general decimal digit representation. Can someone remind me what the general decimal digit representation looked like? So if I have a number y in the non-negative integers or the natural numbers, including the French natural number. Yeah. Yeah, so it's represented as maybe we do something like this. I think that's what we eventually settled down on, right? D2, D1, D0. And I like the way that you said this. So this is, we should call this the Misha conjecture. This is going to what we call a string of how many decimal digits are in this representation? Try again.
N plus what? Plus 1?
Ah, there it is. I love it. Yep, mistakes are the best teachers for sure.
By 1, you know.
Hey, perfect. N plus 1 decimal digits. What did we say about each decimal digit? From what set did each decimal digit come?
What do you call them? What's the notation? 0 through 9?
Yeah, you got it. So the set enumerated element enumeration for that set is 1, 0, 1, all the way to 9. I call that the set D if you had a representation that you wanted to go. Let's do another version of this. So we'll go down a little bit as a little helpful habit. This is Wednesday the 29th, 2020. Can you believe that only took me 3 minutes to do that page? Yeah, I feel like I am just having a great day. I'm seeing you all, so it's got to be a really good day. Love this class. Okay. Can you help me break down what that decimal representation in terms of its actual value, or another way to say that is in power notation? And maybe I can ask Nick, because I think Nick's starting to capture this pretty well.
Which one are you talking about?
So if I were to actually break, so this is a string of digits, right? We've got n plus 1 digits, but those digits actually encapsulate, they encode a physical magnitude underneath, right? So how would I actually get to the physical magnitude in terms of a power representation?
It would be D times 10 to the D.
Yeah. dn times 10 to the n plus...
dn plus 9 times 10 to the n.
Yeah, except that this is kind of funny, right? Because
It is going backwards.
Yeah, it is going backwards. That's a really nice way to say it. All the way down to
0.
d0 times 10 to the 0. These things down here, this was called the index for each decimal digit. What did we know about in these particular indices? What were they pegged with? Position numbers. Very nicely done, Kyle. You've been suffering. That's awesome. And it's my fault. I always like to think about my job as reducing human suffering, but it seems like I cause a lot of human suffering, right? Yeah, so the idea is that it's the position number. What's another way to say position number? the corresponding Yeah, it is the decimal place. Power on the radix 10. And I actually want to kind of quote my favorite, I don't know if it's my favorite line, but it's a pretty damn good line. It's like the decimal place. That's a good line. Because it is. It's just that the decimal place encapsulates that idea in making the person that says that seem a little bit more fancy, right? Okay. Could we write this in summation notation?
Sum. I starting at 0, being an n. Product of the digit I and 10 power of I.
Okay. Yeah. And again, d sub I was in D. 0 less than or equal to d sub I less than or equal to 9. What do you notice about the upper bound of the decimal digit?
The 10.
This is 1 less than the radix, right? Why would I say 1 less than the radix and not 1 less than 10? Yeah, and in particular, I need a beard and a pipe. Could you guess what we might do today? It's legal in lots of places to have a beard and a pipe. Yeah, what are we going to do today?
Radix of 2 instead of 10.
Yep, we're going to look at what happens when we change the radix of 2. So let's go ahead and go, oh my God, we are just flying. And I'm going to keep this one up here because I want to see if you all can guess what a binary representation should look like. And instead of doing our really, really cool thing of looking at examples to build a general, what we might do is see, we've done one general. Can we hypothesize, can we conjecture what the other general form would look like and then confirm via an example, right? It's a very classic mathematical concept. Okay, so let's do what we call the general. Instead of decimal, can you guess what I'm going to say? Binary. Binary. I want a binary pet. Binary. Thank you. Yeah. I'll take any cheap laugh I can get. I mean, some of them aren't cheap, right? In a binary representation, what's the radix? Is 2. Radix is just our way of being fancy about the word base. In all of these cases, for unsigned integers, what type of numbers am I representing? Yeah, the French natural numbers. And another way to say that is non-negative integers, right? Then we represent y as a binary number. Okay, let's go ahead and think about this. How did we represent y as a decimal number? What did we do? We chose
We took the decimal digit and then multiplied it by the place that it is within the number.
yeah.
So like 10 to the whatever.
We chose n plus 1 decimal digits and then multiplied each decimal digit to the corresponding power of the radix, right?
Yeah.
Let us not abuse the number or the letter n. Today's lesson is brought to you by the letter n. I want to watch Count Dracula right now or Sesame Street. Let's say that decimal digit representations are brought to us by the letter n, as in November, and we'll say that binary digits are brought to us by the letter m, as in mangle, but I agree that each binary digit, we might say, call it BM, no, you're right. No, you. No, you stop it. No, don't stop it. Just you keep going. All right. So when we're thinking about a decimal representation, it's a string of decimal digits. In this case, it would be m plus 1 decimal digits. Can somebody fill in Misha? And I don't want to overwork with Misha because Misha knows that I'm cheap and I'm lazy, right? Those things are true. Always. The hardest working lazy man you'll ever meet. What would the corresponding sentence be here? Okay. Up here, we had that each decimal digit had to be in the set of possible decimal digits. The lower one started with 0. The upper one went to 1 minus the radix. So the radix in that case was 10. 1 minus 10, or 10 minus 1 is 9. Could you guess what we'd say about each binary digit? Well, if we call the decimal digit set D, tree. Awesome. Yeah. And B is going to be the set of all 0 and 1. The upper bound of that set is 1 minus the radix, right? Okay. So now I'm going to go over to my friend Nick. Well, who I want to be my friend Nick. I think I still have to earn a little bit of trust, right? Let's think about this for a second. What did we say about each decimal digit? The nth decimal digit, the value that that digit encoded was multiplied by the radix raised to the index. So if I wanted to know the value of a binary string representation, what would the mth binary digit get paired with? 2 to the power of m. Because the idea is, instead of representing in base 10, each thing is now marked by powers of 2. Okay, what's the next one? All the way down until I get 2 to the 0. Whoa. It's kind of intense, right? Okay. Notice a single y in the non-negative integers has at least 2 different representations. Oh God. What are the 2 representations that we're studying? What we call the decimal representation or the binary representation. For now, I'll distinguish what I mean. If I put a sub 10, could you guess what I mean? Radix is 10. If I put a sub 2, could you guess what I mean? Radix is 2. And now this is where I want, did you all bring your metaphorical Rotten Tomatoes? I want you to bring those every time I see you, because you're going to need to throw them at me at least a few times a day. I mean, I hope no student ever throws an actual rotten tomato unless I deserve it, in which case I will happily. Okay, so let's look at an example of what I mean by this. So we'll call this example 6. And why don't we call it example 3.6, because this is lesson 3. So let's consider y in the non-negative integers, which is given by the following binary representation. And my immediate question to you is, how would I have known that this is a binary representation and not a decimal representation? Yeah, it's almost like the person that wrote this textbook wanted to be very, very clear about what that person was thinking, right? Okay, so the number 11, how much is 11 worth? 3. 11 equals 3. Now you're going to ask, where was that pipe you had, Jeff? Right? So let's go ahead and think about this. What did 11 mean in decimal? It meant 1 times the radix raised to the first plus 1 times the radix raised to the 0, right? So this would be, why don't we go B1, B0, just to get our heads around this notation. Though that's the string of decimal digits, what was B1 in this case? 1. What was B0? I tell my youngest son to B1 every day. And he's like, check, Dad, I got that. Thank you for laughing. What does this mean? First digit times 2 to the 1 plus 0th, I mean really this is the first digit, that's the second digit, but digit in the 0th position times 2 to the 0. Let's go real slow. What was the first one? 1. What was the 0th position? And then I'm confused. This is the hardest problem we've solved all day. 2 to the first, 2, 2 to the 0. Well, it is Wednesday, so I guess 2 to the 0 would be 1, right? Yep. Okay, yeah, I always forget about that. 1 times 2 is 2. 1 times 1 is 1. 2 plus 1 is, on Wednesdays, it's definitely 3, right? So when I say 3, what do I actually mean there? I mean 3 base 10. These representations are identical. The underlying value, the thing that I'm trying to represent, is 1, 2, 3. The way in which I code that value is different depending on which radix I capture, right? Okay. Let's take a look at another one. Let me ask this. Are there questions? I have a ton. My brain is just a collection of questions, followed by I'm hungry. All right. So let's go ahead and see. 10, 23. Look at, we are rolling here. When I'm doing mathematical research in the confines of my own home, if I can do a page in 10 minutes, that's like I'm talking with God or something. That's really fast. I told Art this the other day. In my mathematical career, I have spent 3 weeks, at least 60 hours a week, on one sentence. I was reading a paper. The author said, this is trivial. I spent 3 weeks, and after 3 weeks, I was like, yes, this is trivial. You asshole. All right, so let's take a look at another one. Okay, someone want to give me, maybe we'll call it tilde. Let's not do the exact same one. Give me a string of 4 non.
0, 0, 0, 0.
All right, the digit in the most significant bit has to be 1. The digit in the most significant bit. So the digit in position 3 has to be 1.
Yeah, 1, 0, 0, 1.
Oh, okay. No, we just did that in the notes. Yeah. 1, 0, 1, 0. If that's base 10, how do you say that number?
1010.
1010. But this is not the number 1010. It's the number 1010. Base 2. Okay, let's go ahead and look at this. How many binary digits is this number? 4 binary digits, which means what's the index on the most significant bit? Oh! 4 minus 1. Tree says 4 minus 1 is 3, right? So this would be B3, B2, B1, B0. Let's just make sure that we are knowing that those things are. B3 is what? 1. B2 is. B1 is. B0 is. Okay. What did that binary representation mean? B3 times 2 to the 3. This is the really, really special thing about indexing our binary digits with the position value and not the digit number, right? That this index, that the position value index, matches identically what? The power on the base. This will change as the quarter goes on. We're going to do mathematical functions that represent positions there, and those are going to be quite hard. So some of you might be thinking this is easy.
Elegance notation.
Yeah. It is easy, but Rome, or what is it? Rome wasn't built on a pyramid? I don't know. If you live in a glass house, is worth 2 in the hand. Okay. So what does that mean? Well, let's go ahead and break it down. What was B3? B3 was 1 times 2 to the 3 plus times 2 squared plus times 2 to the first plus 0 times 2 to the 0. And then you all know me. I would fail, if I tested myself under time constraints, I'd fail my own tests. Have anybody seen that movie, It Follows? No? Okay. The joke I was about to tell is maybe one of the funniest jokes you've ever heard in your life, but I won't tell it because you don't know it. All right, so here we go. 2 to the third. 2 squared. 2 squared. 2 to the first. 2 to the 0. Okay, so now this is 8 plus 0 plus 2 plus 0. We'll come back to this in a bit. In a bit. We might have. We don't want to bite off more we can chew. So what's the claim here? Yeah. And in fact, think about it this way. This number has 1 8, 0 4s, 1 2, and 0 1s. Because This number has 1, 10, and 0 ones, right? Okay. So I actually have a table that I'll show you in just a bit, but I want to generate this for ourselves. I guess I should do this. This is Wednesday, 1/29, 2020. I hope some of you are starting to get serious about this. One thing I am is a patient man. I have a lot of control over my own brain. Okay, let's do something that looks like this. Let's generate every possible 4-bit string of binary numbers. So let's go ahead and do this. So I suppose this is Wednesday, 1/29, 2020. It's going to be 10:30 a.m. And are we already on page 7? That's crazy. So this is example 8. Let's generate the universe of 4-bit binary numbers. If I have a 4-bit binary number, what might I represent the general form of that thing to look like? B3, B2, B1, B0. What type of number am I actually thinking about? Okay, so we're going to, over here, we'll call this the 4-bit. Could you guess what bit means? Bit means mathematicians and computer scientists are a bunch of lazy bums. That's what that means, right? I only want to write the first 2 letters of that word and the last letter of that word. Yeah.
Is it saying a 4-bit binary unsigned integer a bit redundant? It's like saying a 4 binary digit binary.
Yeah, but some of you are still getting your training wheels on, right?
Yeah.
And now over here, I want to look at this as the decimal representation. What's the claim of each individual bit? What are the choices that I have for each individual bit's value? 0 and 1. Here's the next claim. What does this actually mean when I'm doing something on a computer? Are there a bunch of little computer-sized Oompa Loompas running around, some of whom are carrying 0s and some of whom are carrying 1s? Voltage values. If we're in the active high paradigm, 0 means low voltage, 1 means high voltage. If we're in the active low, al revés, the opposite, right? Okay, could you guess what the easiest string is to start with? Okay, count them. This is the leading bit, the most significant bit. This is the lower one. Let's count the powers of 2. The least significant bit, what's the power of 2 there? 0, which represents in decimal the number 1. So how many 1s do I have? 0. What's the power here? 1. How many, when I have the power 1 on the radix 2, that represents 2. How many 2s do I have? How many 4s do I have? How many 8s do I have? So if I have the string 0000 in binary, what does that represent in decimal? 0. All right. Could you guess what I might do next? Well, when we count, how do we usually, can you go ahead and count with me? 1, 0, yeah, 0, 1, 2. So we probably want to increment up, right? Do we increment from the most significant or the least significant? Least significant. What's my next choice? 1, count them. How many 8s do I have? 0. 4s? 2s? 1s. Okay. How many 8s?
0.
You ever heard this? There are approximately this many type of people in the world. Those that understand binary and those that don't.
I love that teacher.
That teacher makes me feel privileged. Makes me feel dripping with privilege. All right, so what's next?
0, 0, 1, 1.
Okay. What does the 0011 mean? It means take 1, 2, and 1, 1. When I combine a 2 and a 1, what do I get? A 3. Okay. What's next?
0, 1, 0.
What does that number mean? It's a little fast for me. You're going a little fast for old Anderson. What does that number mean?
0, 8.
Take no 8s, take 1 4, take no 2s, take no 1. What's the next one?
0, 1, 2.
Take 1 4 and 1 1. Yep, and then Art just went like this. I thought he was waving at me. My heart fluttered a little bit, but no, he was not waving at me. He was saying that number is 5. How about that one? I don't want the output value. I want to know what does it encode. Take a 4 and a 2. Then, knowing that I take a 4 and a 2, what do I actually get? 6. Okay, one more. 0, 1, 1, 1. What does that encode?
4 plus 2 plus 1.
Take a 4, take a 2, take a 1. If I take a 4, take a 2, take a 1, what do I get? 7. Okay. Please finish this table for yourselves. I mean, I guess I can finish for you. I'm going to straight up say this. Within the next 2 weeks, I expect you all to have these strings memorized in binary, decimal, and hexadecimal. And the reason that I want you to have them memorized in binary, decimal, and hexadecimal is we are going to be interpreting MATLAB strings in hexadecimal. You know what happens if you haven't memorized strings of binary digits and you're thinking like, oh, what does B represent? How do I write B as a string of 4 binary digits? Do you see that pause? That pause tells me that I need to have you memorize that. Yeah. So please finish that for yourself right now. I would expect every one of you to get a piece of paper out. If you have it memorized, then write it down. If you don't have it memorized, then generate it from logic, right? And I'll do the same thing as I'm waiting for you. And I'll actually do the entire thing from memory. If you've already finished this, then see if you can generate for yourself a general hexadecimal representation first. If we call decimal D sub n and binary B sub m, could you guess what you might call hexadecimal? H sub yeah. H sub L? Is that what you feel my class is? Jeff, your class is makes me feel like H sub L. That comment makes me feel like H sub Evan. Out of curiosity, if I made you the following bet, can you, off the top of your head, tell me, without thinking about it, the hexadecimal representation of 13 in both binary and hex? How many of you could tell me without thinking about it off the top of your head, and then bet the following wager? If you get it, I give you $100,000. But if you don't get it, you give me $100,000, and you actually pay me. Okay. Okay, so 3 of you? Okay, so this will be, in that case, the 3 of you that have those, my challenge to you is to see if you can come up with a general formulation of hexadecimal. And see if you can make a connection between N, M, and L. What is the relationship between N, M, and L? So if I have a 4-bit binary number, what is the minimum number of decimal representations that I can, so in this case it would be 2, right? If I have an 8-bit binary number, it's 3. Why? What's the relationship between M, N, and L? For the rest of you all, this is a good exercise. I will be teaching every single one of you in this class that memorizing this stuff is a very powerful thing to do, for me anyways. And since I'm teaching this class, you're kind of trusting that I'm not a crank. Well, you all have kind of seen that I am a crank, right? Just one that smiles a lot. Some of you might be wondering, how many of you have finished that table? How many still are working? If you finish that table, go ahead and go over to MATLAB and CLC, would you? And then I'd like to set u int 8 of the number, I don't know, 12. And now I want you to do something. Go ahead and format compact. And now I want you to format hex. And now I want you to type y. So let's go. If you haven't finished the table, I want you to finish the table first and foremost. I want that full table finished. And in fact, if you wanted to get a tattoo on your inner arm, yes, you can use the tattoo as notes on your tests. Please know that I allow up to 12 pages of notes, single-sided, so you don't have to get a tattoo. But if you wanted to, yes, of course, you could use that on every test you ever use. Right? Okay, so let's do this again. Go format compact. What does format compact do again? Shortens it. Okay. And then go ahead and set y equal to u int 8 of the number 13. What do I mean u int 8? Forget 13. Let's put 0. What does u int 8 mean? Unsigned integer with how many bits? 8 bits, which is 1 byte, or 2 nibbles. A nibble is a 4-bit string, right? So 2 nibbles means 1 byte.
Is that actual terminology?
Yes. It's not, I mean, it's not my terminology, but yeah. I stole that from somewhere. Check this out. When I format hex, could you guess what hex means? MATLAB is going to give me a hexadecimal string of the binary digits underneath. So if I go y, how many binary digits is y? Eight. How many hexadecimal digits is y? 2. Check this out. Let's go back over to our screen because some of you might be thinking, what the hell? Check this out. Let's go y2 is equal to u int 8 of 13. Could you give me the number 13 in a 4-bit binary representation, please? Yeah, that's exactly why I did it, Jonathan. So you can look back at your notes. What is the number 13? Well, it must be 8 plus 4 plus 1, right? So if it's 8 plus 4 plus 1, it must be 1101, no? Okay, check this out. Let's go back to this thing. Sugar, that's not the thing I want to go back to. That's the thing I want to go back to. Hexadecimal, let's just start counting up. Could you guess what the radix is for hexadecimal? Radix is 16. What's the radix for decimal? What's the radix for binary? What do I do when I have a radix 10 number? Each decimal digit can be one of 10 symbols, right? The moment I max out on symbols, I then have to add an extra decimal digit, no? Okay, so let's do hexadecimal. Could you guess what symbol we use for 0 in hexadecimal? 0. Could you guess what symbol we might use for 1? 1. 2. 5, 6, 7, 8, 9. If it's hexadecimal, how many symbols do we need to represent one digit? Up to 16.
Who wants to come up with more numbers, so let's just use letters.
What letter should we use? Okay, so maybe we use the letter A. Uppercase or lowercase? Well, let's see what MATLAB, this is a MATLAB class, right? So we might call this one A, which is really cruel because what's the next one? B, C, D, E, F. Oh, sorry, you can't see that, huh? And then we'll take a break in just a second. We've done some majorly good work here.
Ready the line again.
What's that?
Ready the line again. The rookie line? Yeah,
Oh, yeah, yeah. I like to come right up against the rookie line and then step back away, right? So if I give you the letters, so check this out. MATLAB told me that the hexadecimal representation of the number 13 in binary. Well, let's think about what the representation was of 13 in binary. I guess it was 1101, right? What if I have an 8-bit binary number? How many bits is this? 4-bit, right? What would I do to maintain the same value with 8 bits? Make the most significant 4 digits. This is still a binary representation. It's just a binary representation that encodes more information, right? That can possibly encode more information. But what was the claim about this 4-bit string? That 4-bit string in hexadecimal is encoded by the symbol 0. This 4-bit string in hexadecimal is encoded by the number D. Now I'm confused, which means I'm doing my job well, right? My job is normally to confuse my students. But if it's gone so far that I'm confused, then I should get a raise, right? What was a variable again? What was a variable?
Thing encoding 3.
Yeah, okay, yeah. So a variable was this concept that 3. I gotta keep spin that out a little bit, and then yeah, it's got a name.
Address. And it's got some bits.
Okay, so a variable has a name, symbolic representation. In this case, let's go ahead and clear all. And then let's go ahead and, yeah, CLC. Okay, so here we go. The equal sign there, what does it represent? Oh my goodness. Just a little bit louder now. Just a little bit louder now.
Assignment.
I know, but
Assignment.
assignment, okay. Assignment, what does that mean?
Consider the value of y. Represent the value of y.
So I'm going to give this variable the representation that humans think about as y, right? Okay. How many bits am I dedicating to this variable?
8.
8 bits. Because the data class is uint8. What does uint mean? Unsigned integer. Could you guess how to break the uint8 data class?
So raised to the 8th power.
Oh, yeah. That's true. Oh, yeah. 2 to the 32nd. Oh. So a variable was a name, a address in memory, and a value. What has MATLAB produced that I'm actually conscious of in this case? MATLAB produces the name. When it gives me this representation, it's telling me the value of the bit string actually stored in memory. Let me repeat that in a different way. It's giving me the voltage values that are down in the deep bowels of my computer, coded in hexadecimal. Did it give me the address? Is that something that I, as the coder at this level of coding, have access to? Nope. I don't know where that is in my memory. MATLAB knows where it is. My computer's, what they call operating system knows where it is, but I don't, right? But I definitely know that if I want to refer to that variable, I'm going to refer to it as the letter.
MCA.
And then I also know that if I took a scalpel, opened the computer, found the actual string in memory, and then measured the voltages, what's the string of voltages for, I don't know, uint 8 of 13?
Probably 0 if you just do the
Read them. We just did this. What's the string of, how many voltages do I measure for a uint 8? 8 voltages. So let's do the active high paradigm. Active high means zeros are low voltage, ones are high voltage. Read the string for me. Low, 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 high, high, low, high. And that was big endian. Little endian would be opposite, right? Yeah, don't worry about those. We'll get to that. But some of you might be thinking what I've heard critics say, this guy ain't teaching me shit about MATLAB. Actually, we are now into the inner workings of how MATLAB works. When you write syntax, my expectation is that you know what the hell that syntax is doing, whether or not you remember what the syntax is. Right? Okay, should we take a break? It's 10:56. What time are we going to start again? 11:06. Sold to the man in the red sweatshirt. I don't know who said the man in the black sweatshirt. Okay, come back at 11:06. We'll get started again.